Thanks for that, JP. Common flaws. What do I mean when I say common flaws? Are there any tokens left in your contract when it's trying to exit? Well, Reach will tell you that. Hey, you made a mistake here. There's extra tokens in the contract when it's trying to terminate, and that is a security flaw that exists in other languages. That Reach uses the verification engine to engineer away, to abstract away the possibility of that ever happening. It covers a lot of other things too. We'll get into some more of them later. How do we think through a Reach app, right? So Reach we're going to build our contracts in Reach, right? We're going to allow those contracts to connect to the consensus network of our choice. Right now, we support Algorand, Conflux, Ethereum, and all of its layer 2s. Right? So if it's EVM compatible, Reach is also compatible there, right? So the structure of a Reach program. This is how we're going to start to think about how to work through a Reach app, right? The smart contracts enable the participants to interact and complete transactions on the consensus network, right? Our participants are made up of this interact interface, which has the participant itself and then the participants' classes. These are the methods and values that particular participant can access, right? Participants are logical actors that participate in the decentralized application. They're associated with an account on the consensus network, right? When we say consensus network, we mean blockchain, right? We mean, in this context, we mean a blockchain. When we just say blockchain, you know, most people are going to think of Bitcoin, but there are many different blockchains, especially smart contract platforms like Algorand, right? This is primarily what we're going to cover today. So as Reach grows, more blockchains are going to be deployable through Reach, and it's going to reduce that need to understand each of those low-level programming languages, right? Like Solidity or Teal. By defining these participants that we talk about and the way that they interact, developers can create this participant interact interface, and that's how the backend smart contract is going to interact with the actual application, right? So Reach is very similar in syntax to JavaScript, right? With minimal training, we say a full stack developer can write decentralized applications with Reach in 3 to 4 weeks. Those of you who've been through some of our other programs understand that once you start working with Reach and you really get the wheels turning, Reach starts to feel very familiar, and you can start to think about the high level of what your contract needs to do as opposed to the low level actually interacting with the hardware that needs to do it with, right? So that index.rsh there in the bottom left-hand corner, that's what we say it composes our backend. That's our backend smart contract, right? We don't like to think of developing a smart contract. We build programs that focus on how the participants will interact with that smart contracts interface. And then Reach compiles that program into a smart contract on your desired consensus network. Again, we're thinking about how the value, or how the value and how the information is passing back and forth from the people that are actually giving it to the smart contract, and how the smart contract actually interacts with that value, right? So after we compile our backend smart contract, our RSH file, it compiles down into our build folder, into a file, an index.main.mjs, a modified JavaScript file, right? This is how those files are related. Your RSH file with the functionality from your front end is going to become your index.main.mjs, and that's where we're actually going to reference. And I'll show you later when we get into the code how we import that file from the build folder. So again, the index.main.mjs includes the actual backend, the compiled backend RSH, and all of the smart contract bytecode, right? That bytecode is actually what's going to be sent to the consensus network. That bytecode is what's going to interact with your Algorand node, right? So the verification engine that I discussed earlier, it runs at compile time to validate that smart contract, right? It basically creates these mathematical theorems and proofs to confirm that the program is completely secure, right? It tries to break your program in every way possible, and it does not compile if it finds any flaws. You start to build more robust reach contracts, that verification engine starts to feel very familiar. It starts to feel very comfortable to be able to check. And that's one of the keywords you actually use, check. Check this is okay. And you start to, as a programmer, you start to feel more comfortable relying on that verification engine to do that mathematical proof work for you, right? So the developer creates a front end for the reach dApp, right? We've talked about the back end compiled smart contract and the bytecode, but the developer needs to create a front end for the app interface, right? Where are our participants actually going to interact? Where are they going to input this information? Where are they going to see messages that relate to the information that's moving around in our smart contract? That happens in our front end file, right? In this instance, we're looking at index.mjs. Again, that's that modified JavaScript. It allows us to create these quick these quick command line programs that we can just test a bunch of different cases really quickly. So we can create that front end. Typically, we create them in JavaScript, but we also support Python, C# and Go languages with the RPC server. And I know the Reach team is hard at work to continue integrating as much as possible into the Reach platform. So the way that we start to look at how the front end interacts with the back end, we say that it mirrors the back end. We say the front end mirrors the back end. Why do we say that? Because the participant back end, it shares the same method signatures or function signatures as the participant's front end, right? We use the front end to implement the actual functionality, but we declare those method signatures in the back end. If those don't match, our Reach compiler is not going to like that. We're going to have to make some fixes that make sure that those methods match. That's why we say that it reflects the back end, right? The front end reflects or mirrors the back end. So the Reach JavaScript standard library provides support for both the front end and the back end, right? We call it in the front end, and accounts and addresses that we use there are almost completely interchangeable, right? The terms that I'm using there, the account, the address, these are completely interchangeable. So a contract is an account that can also store values, right? It's consensus state. They receive and they process publications and modify the consensus state as needed, right? The contract may also transfer network and non-network tokens, right? So these contracts may also provide like mappings between the address and a certain value, or provide a view into the window of the consensus state, right? And this graphic here shows a little bit more about the interaction between the front end and when we import the standard library, what sort of helpers are we getting with that, and what are the key abstractions there that help us interact with that consensus network, right? So a complete Reach decentralized application, right? It includes that front end. It includes the backend RSH smart contract, right, which compiles down, like I said, to that index.main.mjs, and it includes the JavaScript, the standard library in the front end, right? This is what we call our full Reach app, right? And this is how the interaction between that backend file, that front end file, and all of the tools that the standard library comes complete interacts with the actual consensus network. We'll get into the details more as we get into the code a little bit more as well. So this is that account that we talk about, the term account, right? So we're saying that the account is a wallet, right? It's an actual wallet, which is we say is your window into the consensus network, into the blockchain, because your wallet is your address. It's your ID on the blockchain. We don't know what your name is. We don't care. We want to know your account. And on Algorand, it's got to match the ARC11 standard, which I believe Reach mostly supports MyAlgo and Parallel wallets. But if we talk about interoperability, Ethereum Reach must match with the MetaMask wallet, right? Again, these wallets, that's your ID. That's who you are on the blockchain. So the smart contract is then deployed to the consensus network. This is where the Reach standard library comes with these tools that help us to deploy the actual contract, that actual bytecode out onto the network, right? These contracts live out on the network when they're in use, right? So this is how the contract here is going to deploy out to your desired consensus network. Again, today we're talking about Algorand. So the contract and the standard library actually holds a couple of tools that help us deploy to that network. That's why we say Reach is it's a platform. It's a blockchain development platform, because it's more than just a language. It comes with that compiler, that verification engine, and the deploy tool that we're talking about here. So we deploy that smart contract out to the network. The network includes the contract inside of a new transaction block. Right now, it's out there on the blockchain. Right. This is why we say there's zero budgets for bugs in blockchain, and why Reach has so much abstraction around the security of your smart contract, because we can't just modify code that we've sent out. We can't just roll back our latest release and make adjustments to code that lives out on the blockchain, right? This is why, again, why we say there's zero budgets for bugs, and why we love the verification engine that comes with Reach, because it helps to minimize, it helps to eliminate those sort of common bugs that we've seen happen already in a lot of blockchain networks, and some of these flaws or these contract flaws or vulnerabilities, sometimes they're called, have caused losses in the millions and millions of dollars, right? So what happens next? The smart contract lives out on the network. The participants attach to the actual contract and interact via the contract, right? And we'll talk more about how they interact with that contract once we get into the code a little bit. But the participants can use that contract any way that the program will allow it, right? And the Reach decentralized application will connect them to that through that front end interface, where typically if you've used decentralized applications in the past, you get like a wallet interface that pops up, right? It says, who are you? Input your wallet address, so that we can attach you to this application, and we can attach that to the network, right? So that's basically how we start to look at the life cycle of a smart contract, the way we start to build it out, starting with our back end. We work up into our index.mjs file front end, and then we connect that to the Reach standard library, right? We deploy our contract out to the network, and then we allow our participants to attach to that contract via their wallets, right? Again, on Algorand, MyAlgo, Parallel wallets are best integrated with Reach. And they attach to that contract via the wallet, and then they're allowed any functionality that the decentralized application allows, right? So that is sort of a overview of what it looks like to start thinking about a Reach application, how to build a Reach application. And we'll start to get into a little bit of the install here. So here is a QR code that should link you right to the Reach docs for installation. And while I leave that up, if anybody has any questions, you drop in the chat there, I can get to just about sort of general architecture. But again, I love to actually get into the code. I actually start getting into scaffolding and building it out, and you'll start to make these connections a little bit easier. Personally, I'm a very big, learn by doing, right? So actually getting the code out in front of me and writing the participant interact interface and how it actually interacts with the contract, right? So
no questions in the chat yet, but I'm monitoring it. So if anyone does have a question, put it in there, and I'll help you if I can, or we'll address it to Nick.
excellent. Yeah, thanks, JP. These are the key components that you need to have installed to install Reach, right? You need Make, you need Docker, you need Docker Compose. Docker helps us create this container that we can connect Reach to your consensus network. If you're on Windows, you need to have a WSL2 installation. And just to briefly touch on that, we get a lot of questions on this. WSL is actually going to create a Linux system inside your Windows machine. It's not the same as partitioning your hard drive, but it's similar, such that you will have a Linux OS on your machine. So when you interact with Reach after installing this WSL and this Linux OS, you need to interact with Reach from that Linux distro, right? You should not be interacting from your Windows PowerShell at that point or anything like that. So I get a lot of questions there. I want to stop and take a second to address that. So scaffolding of a Reach app, right? Some of the things that we're going to use a lot. Reach update. Reach updates the language it's bi-weekly, every other week. We do updates to the Reach language in the standard library. This command will update for you and ensure that you're up to date on the most recent release. Reach init is going to create a boilerplate for you. Reach init is going to spin up two files, your index.rsh and your index.mjs, and then it's going to actually already include the code that you need to just get your boilerplate going. So after running Reach init, you can connect to your consensus network, and you can run it and get some basic output on your console, right? So I want to go into the modes here real quick, because this is a kind of a key aspect of Reach. And I want you to have a kind of an overview here before we move into the actual scaffolding. So we're gonna initialize our application. Before we initialize our application, we're gonna define what our constants are, right? We're gonna start talking about defining those method signatures, those function signatures. And then when we initialize our app, we're actually gonna be able to, we're gonna start walking through the steps of our app, right? When I say step, I reference the state of your contract. If you write an app, there are different states where your contract knows different values, and it expects certain things of those values at certain points. So after we initialize our app, we're going to move into those steps, right? And those steps can move in between local step, which is me interacting with the computer, right? It's me, the user, interacting locally with the computer, right? Before we move that information out to the consensus step, right? We move that information out and publish it to the blockchain so that we can continue through our steps. And you can think of this as just accessing information at different states of your program, right? There are certain times where I, the user, need to input information to the computer. I need to input information to the smart contract. That's going to happen in my local step, right? Maybe the program needs to compute a few things and make a few moves without the user. Well, that's going to happen inside your step, right? And anytime we're talking about publishing information to the blockchain, we're talking about a consensus step. We're talking about an area of our program where everybody agrees what's happening, right? If I publish the wager is 5, well, we all agree the wager is 5. If anybody disagrees with that, it's going to have issues with our application. It's just not going to work, right? Because our consensus steps, we all agree on the information in those consensus steps. So that's a high-level overview of these steps. And as I work through the code, I'm likely going to touch on these a little bit. So I wanted to give you a little bit of outline on that too. So I think we're going to go ahead and move into scaffolding. So give me just a second to finish getting set up here. Okay, can we all see VS Code window there?
Looks good.
Looks good. Okay, at this point, I've gone through the quick start docs. I've installed Reach on my machine. I'm ready to start building, right? I'm on Windows. I've had to install WSL2. I've had to install my Linux distro, and now I'm operating from inside my Linux machine, right? So the first thing we're going to do again is we're going to go through just the scaffolding of a Reach application, right? So we're going to start with the backend file, right? That's our index.rsh. The backend is our actual Reach contract, right? And then I'm going to also create our MJS file here so that I can kind of get out of here and actually get us into our files. So I've got index.rsh, index.mjs. We're going to start building the index.rsh file. So at the top of every Reach application, we need to let Reach know what version of Reach are we writing in. Right now, 0.1 is the right answer there, right? And then we're going to create our actual Reach app, right? So how do we do that? We export const main equals a Reach app, right? Just a quick touch on end of line characters. Reach doesn't require them. If you find that you're jumping around to include them from your experience in past languages, don't get too upset. You can avoid them if you'd like. So now we're going to define who is actually interacting with our Reach app, right? Well,
Nick, can you increase the font size there 1 or 2 times?
Okay, so I wanted to.
Should be like a Control Plus or something like that.
oh, is
There
that,
you go.
is
That's
that
good.
better?
Yeah, you don't want to blow it up too much, then we can't see beyond the line.
Yeah, right.
Thanks.
Let me know if I need to go the other way. Okay, so Alice and Bob, these are our common names. We're talking about cryptography. We love to keep it old school with the names here, and so we'll call our first participant here is Alice, right? We're going to say const Alice equals a participant in our Reach app, and there are different types of participants, but for this scaffolding, we're just going to cover participant, right? So now here is where we're going to say is Alice's interact interface, right? This is where we're going to we're actually going to create the method signatures that only Alice deals with. The information that only Alice deals with is going to happen inside here in this participant interact interface. So who is our other participant? Again, it's going to be Bob as our other participant. And then we're going to specify Bob's interact. I do make mistakes on comments often because I'm typing so fast, I don't care if they're correct. But okay, so here's where we talked about creating in the different steps. We're going to define our constants. What information is just Alice going to provide to the contract? What information is just Bob going to provide? And then we're going to move into the initialization of the app. This init does that. This is us telling Reach, okay, let's start stepping through our app, right? The first person to publish information is going to deploy the contract to the network. Remember, we said we need to deploy it so that it lives inside of a transaction block. When we publish, that's what is going to happen here. We're going to actually deploy the app to the consensus network. We're going to commit. Commit is us moving from that consensus step. Remember the graphic, it's us moving from the consensus step back into our program step. Again, just a different state of the application, right? We're gonna, again, this is just the scaffolding. This is what we need to get Reach to run, to output, right? So we're gonna say Bob is also gonna publish here. He's gonna publish some information, right? Bob is also going to commit to this information. And then we're just going to go ahead and exit our contract. This is very scaffolding, boilerplate. Everything, when you start getting into the meat of the actual application and you're going to add information, you know, Bob's going to tell us that there's a wager. That wager is going to be an unsigned integer. This is how you would do that, right? But just for the scaffolding purposes, we're going to get this thing out and get it to run. So that is our reach file. I'm going to save that, jump over to index.mjs. Index.mjs, again, is our modified JavaScript. This is our front end, right? This is where our actual user is going to be inputting information, right? Where we're going to be displaying information. So the first thing we're going to do is load the standard library. I use autocomplete there because I cheat a little bit. But we're importing the standard library from reach standard library, right? What do we need next? Next, we need to import everything as the back end. Again, this is what we'll reference here as back end. From, where are we pulling it from? Well, remember, our smart contract was compiled down to the build folder in a file called index.main.mjs. Well, that's where this is, right? So if for example, I did this, Reach isn't going to like that, because right here we're saying, well, it's called main with a lowercase m. Well, here you're trying to import a file with an uppercase m. So this is where that relation comes from. You're actually importing the export here. So you need to make sure that these two match, right? That's where we're importing our backend. Right now we're going to create a constant, and this is just going to load the actual standard library for us into that constant so that we don't have to reference it like this. We're going to set that to a process environment. Right? Well, if we're going to create accounts for our users, we need them to have a starting balance. So let's create a constant for that starting balance. And let's say we want that to be 100. 100 algos. Well, the network deals in micro algos. So we're going to use the standard library function called parse currency to take that 100 and parse it down for the network. We'll cover going back the other way here in a minute. So now let's actually create those accounts. Let's say account Alice, and there's an account Bob. Well, we need to await that the standard library creates us that test account. This is a testing feature when you get into actually implementing wallets. You won't be spinning up new test accounts. You'll be importing those accounts from the actual wallet. So here we'll use that starting balance to fund those accounts. And now let's just give us a console log that tells us where we are. Well, we've created their accounts, so let's say hello, Alice and Bob. Okay. We're going to include another message that lets our user know that the contract is actually launching. Okay, these next few lines are really important. This is where we're actually going to use the accounts we have, account Alice and account Bob. And we're actually going to attach them to the contract depending on who they are, right? So now let's say, well, the first user deploys the contract, and that is Alice, right? So we're going to call it CTC Alice for contract info, right? So we're going to use Alice's account and this contract function to attach it to our backend. Well, remember, here's our backend, right? This is where we're referencing that backend. So now Alice's account has attached to that contract backend, right? Well, the other participant we have is Bob, and we need Bob to attach to Alice's contract now. This part is very important, right? We want Bob to attach to the backend that also has Alice's contract info. Right? We're going to let that know that we've got everybody attached, and we're going to go ahead and start our backends. Now, the next section here is going to be so that we can actually await several promises at the same time, right? Several resolutions at the same time. This is a standard JavaScript here. Await the promise of all, right? I can feel JP's pain here because I do also really enjoy these messages as I type, but as I present, it's right in the way of what I'm trying to show you. So I like to add those right there just to make sure I don't forget. I don't like going back. Okay, back end of Alice. Well, that's that Alice contract info we're going to send in there. Right? And then the back end of Bob, take Bob's contract info. Okay, what are these? These are those participant interact interfaces. Interact objects in the front end, I believe we call them otherwise. But this is where we're actually going to mirror those functions, right? We don't have any functions back here. Remember, we're just going to create a boilerplate. But I believe we need to import at least this. Don't forget syntax. Do the same thing here. There is a different way to handle this, but for the boilerplate feature, we sorry about my notifications there. So many different messaging apps that are always dropping notifications to me. So, okay, so we have our interactive objects here for each of our different participants, for Alice, for Bob, as it relates to their backend contract info, right? So we're going to go ahead and give us a goodbye message here. So let us know where our contract is. Double check for any lost semicolons. Okay, that's our boilerplate, right? I'm gonna go ahead and save this one into my terminal. You can also run these files from your Ubuntu terminal, but it's so much easier from right inside here, inside VS Code. I believe I have this one in a folder called present. So I'll get into my present folder. Show me what's in there. Index.mjs, index.rsh. Okay, well, that's good. Those are the files I made. Well, we need to tell Reach which network we want to run on. We want to run on Algorand. Why do we want to run on Algorand? Cheap, fast, secure, all of the above. Okay, so now Reach knows, okay, well, we're going to try to connect to Algorand here. And now we're just going to say Reach run. And if I haven't made any mistakes, oh, did I save it? I did. Index.rsh does not exist. Oh, I wonder why. Okay, no problem. Let's go back to the last folder. Let's call this test. Now I'll get to show you the other feature. What happens when we use reach init? Well, reach init created this same folder for us. Let me get some of this out of the way for you. Remember, I called this one present test, right? So we have the same participant interact interfaces and the same kind of boilerplate here. Now I'm going to see what our output is. And this is the same code that I actually just wrote. So let's want to compile first to make sure it's there. Okay, well, there's the verification engine we talk about, verifying the knowledge assertions when all participants are honest. Here, when all participants are, no participants are honest, right? It's going to check that for us as well. It says we check 7 theorems, there are no failures. Okay, so I think we're okay now with our our boilerplate. Of course, when you're presenting, it's not going to work on the first try, so bear with me on that. Okay, so here's Reach spinning up your container to the Algorand network. Here is Reach running that front end, those console messages we talked about. Hello, Alice and Bob, launching, starting backends, and then goodbye, Alice and Bob. So here it had to jump to the back end, do our couple of publishes that we have inside of this RSH file. I'll drag my terminal window down here so that we can see that. These are actual actions that need to happen in the consensus network. We'll publish those, and that'll take us just a second or two, especially on Algorand. And then we're gonna goodbye, Alice and Bob. So that is the boilerplate of a Reach application. That is your, let me get this out of the way here. That is your backend smart contract RSH file. Starts with Reach up here at the top. This is where we're gonna export our Reach app. And then it goes over to the front end file. I'm a little bit nerdy, so I'm gonna keep that one in the front because it's the front end. Okay, so then we get into here, and here's where you're actually seeing your console messages. Here's where you're actually asking your participants to do something, right? Okay, great. So that is the scaffolding of a Reach app. Take any of the questions we have on scaffolding there before we move into the actual NFT demo, which is a little bit more of a real world sort of use case of what a Reach application will look like.
Nick, I had a question. So in our promise in our front end, some of the times we're calling the contract using contract.participant.alice, like in previous documentation as well as in the course previously. And then in this, we're running backend.alice and then putting the contract inside. I'm just kind of like curious is the difference between those, or if it's the same thing and just a different way to write it.
Yeah, so it's similar. It's just a different way to write it. So it can work. And I know exactly what you're talking about because I had that same thing when I started learning Reach myself. Well, what's the difference here, right? It's really just the difference of how we want the contract to go off, especially when we start talking about different threads that can be running, who's doing what at what time. I mean, for this like super simple Reach application, both of our accounts, we want them to do the same thing at the same time go, right? So once you start kind of packing on functionality, you're gonna change the way you write that. So it's a good catch on your part because I do understand where exactly you're coming from, but the short answer is that there's just different ways to do it. All right, so let's get this boilerplate stuff out of here. Again, we're going to start with RSH, MJS. Make sure I got my notes up here correctly. I'm not doing this off the cuff if you thought I was. Read my notes. I like this example because we're really going to get into exactly the features, the power of the features in Reach. This is one of the things that as I started learning Reach, I could not really wrap my head around. The more features you pack into a Reach application, it seems like the smaller it gets. We're going to write this entire NFT auction app and it's going to be 50 or 60 lines of Reach code. I think it's 51 or some lines of Reach code, which is just incredible. And it will have a completely different structure than what Connor, if you've been through the other materials we've had, okay, you just saw that one. Well, this is also going to have a different structure than that. So
yeah, the docs, every time I click on a different set in the documentation of examples, it's some different way of doing it. So that's why I was trying to figure it out.
Yeah, at first it's about understanding the way that we interact with our Reach contracts and the way that we start to build the functionality. But then once you start to understand that, it's about, okay, well, how do I pack on a feature? How do I add this feature? And as you're adding these features, Reach is abstracting away so much that, oh, well, we know you wanted to do that, so we're going to give you parallel reduce. You didn't even know you needed it. But once you learn about what it is, you're really going to appreciate what I refer to as all the time as the abstraction of the Reach language, right? It's built for these smart contracts. So one of the things that we really recommend is to start with program design, to start thinking about how you work, how your contract and how your front end interaction is actually gonna be before you start writing code, right? So the goal here is to get you up and running on a prototype that has a real use case, right? And we want to show you the best practices for building decentralized apps with Reach. So that's exactly what this is going to do for us. Okay. So I'm going to go back just a little bit to the modes of the Reach app, because again, this is like the kind of a key portion of this for us. So app initialization, right? We're actually going to start doing things here. We're going to start working through the steps of our app. Local step. I, the participant, need to input some information to the application. That happens between me and the computer, right? Step. What is step? Step is that program state. We're moving between one state of the program to another state of the program. You're telling me what that state should look like. Consensus step. These are public steps that enter these transactions into the network, into the blockchain. Actions executed here are immutable and complete public knowledge, right? If we're all familiar with the blockchain, this is where that information goes to the blockchain, right? So the NFT auction that we're going to do here, it involves a creator who establishes the sale, and it involves buyers who bid on that NFT in algos. If the bid is successful, the decentralized app will hold those algos, and bidding is only allowed while the auction is active. So if the second bidder comes in and outbids the first one, the contract automatically refunds that previous higher bidder, and then it secures the funds of the now highest bidder, right? So the contract's always going to hold the funds of the highest bidder, right? At the end of the auction, the highest bidder receives the NFT, and then the contract actually transfers the funds to the creator, right? So we're going to evaluate the problem we want to solve first. This is that NFT auction, right? We're going to itemize the data definitions and the types that go with those. And then we're going to make a list of the participants and how they actually interact with each other and how they interact with the contract itself, right? We're going to write all assumptions we have about the business logic. How should this interact? How should this dApp actually work? We're going to write those assumptions into our logic, right? Assumptions are for that verification engine, right? Absolutely key to understand how to write good assertions, right? Good assumptions. So the problem that we have for this auction dApp, collectors of NFTs here, they desire a secondary marketplace to sell their assets, and buyers, they desire the desire to actually purchase these NFT assets, right? Sellers, they must be able to create a new auction for each piece of artwork, right? The NFT needs to be held inside the contract after the auction begins and until the auction closes, right? This helps keep it secure in the actual logic of the contract, right? So for each bid, the new bid must be higher than the previous bid, and then for the last bid will be refunded to the previous bidder, and then that new bid will be recorded as the highest bid and actually, remember, held inside the contract. So at the end of a successful auction, the highest bidder is going to receive the NFT, and the seller is going to receive the full payment amount in algos, right? So let's actually start writing some code. Data definitions, right? The necessary data points and their types is where we're going to go here now. So in Reach, these global constants can be defined using the const keyword, and these localized backend methods are defined in the participant interact interface. Remember, the backend is that .rsh smart contract, right? This dictates the app's communication model, right? So the methods in each participant's interact interface are going to mirror that front end interface. So let's go ahead and define the methods in the participant interact interface. Remember, first we need to start with reach version 0.1. I'm actually going to go without those here. And then we need to go ahead and define our reach app. We're going to export const main equals reach app. Okay. Who is involved? Well, remember the last one was Alice and Bob. Well, in this one, we need a creator who is a participant. We're going to call them creator. And here's where we're going to define the data definitions for that creator. Well, actually, is that, yeah, that is correct. So, okay, what does the creator actually need to do? Well, the creator needs to tell us about the sale. They need to say, what are we actually selling? Give us the information about it. Well, get sale is a function. That's how we denote the function there. It is a function that takes in no arguments, and it's going to output us an object. It's going to return us an object. Okay, this object, what is this object going to have? Well, it's going to have the NFT ID number, and in reach, tokens are a special type of data. So we will say that NFT ID is a token. Well, what else does it need? Well, if I'm the creator, I'm going to set a minimum bid. What's the least that I'll let this go for? And that's going to be an unsigned integer. It's also a primitive in reach. And then I'm going to define how long I want this to go on. How long do I want length in blocks for this sale to go on, right? Okay, well, that is get sale for the creator. It is a function that takes in no arguments and returns an object that has all of our data. Great. What do we need to do now? Well, we need to notify or let the contract know that the auction's ready. Well, this is also a function that's going to take no arguments, and it's going to return a null value, right? We need to see the bid. Who's bidding? What? Well, this is also going to be a function, but this one's going to take in the address of our bidder and the number that they bid. It's going to return that. Okay, so finally, we want to show the outcome. We want to know, what do we want to know in this outcome? Well, we want to know the address of the winner. We want to know how much the bid was that won. And this is also going to be a null return. I apologize for that. Okay, that is our creator, right? So we're going to give them a get sale with all our information. We're going to let them know the auction's ready. We're going to see our bid, and we're going to show the outcome. Now, this next part, we're going to see a new type of participant. Well, they're a bidder, but we're going to call them an API. Right? We'll get a little bit more into what APIs are, but basically what APIs allow us to do is create a repeat bidder with all the same functionality. So instead of saying participant B, C, D, E, F, I can say API bidder. Every person who needs to bid on this contract is only going to be able to have this functionality, right? We don't want the bidder to be able to set the information about the sale. We want them to be able to bid. So the bidder gets to bid. Well, the bidder gets to bid using a function where they input the unsigned integer for the bid. They are going to return a tuple containing the address and that's the only functionality our API is going to do, right? So now that we have what we see here are data definitions, right? The NFT ID is a token. Here is a bid function that we're going to use in the front end, right? That's our data definitions. Now we're going to go ahead and initialize the application. And remember, this is where we're going to start working up through the steps of our application. So line 17, there's that initialize. right? So now let's set up the initial data definitions that happened in the front end, right? Remember, these are going to mirror each other, and I'll show that again here once I get through a little bit more code. But this is our index.mjs file. Remember, this is our modified JavaScript front end. It's going to execute on the command line. Just a second to get this up here. Okay. So, MJS file. Well, first, again, let's start with our imports. What are we importing? We're importing the standard library. You can type all that out if you like, but again, I tend to cheat on these when reach allows. Import everything as the backend from where? Well, remember, it goes in build index.main.mjs. So if you always call this main, you can always use this import. Okay, so lines 4 and 5 here, we're going to say the standard library. Remember, we're just going to load it here so that we can use this constant. We're going to give ourselves our starting balance. Again, we need to create test accounts in this environment. Those test accounts need to be funded with money, with algos. So we're going to fund them with 100 algos and allow the standard library parse currency to take that down to micro algos for us, so we don't have to make that calculation in our heads. Now we're going to create a test account for this creator. Again, we're going to need to fund that with our starting balance here. So let's give us a console message here first that says console log. Well, we're creating a test account for our creator. Again, this is not going to be the case if you have someone who's actually deploying your contract via wallet interface. Let's give them a creator account. And let's say we're going to wait for the standard library to tell us about its new test account. How much do we need to fund it with? Well, we're funding it with our starting balance, right? Again, alternatively, you can cut all that out and stdlib.parse currency down to 100. But if you need to refer to this ever again, it's much easier just to say starting balance, right? So let's line 7 and 8. Let's jump down here in 10. Let's create the NFT now. Let's actually have the creator actually create us an NFT, right? So again, we're going to let the console know what we're doing. Well, we're having the creator create a testing NFT. Okay, how do we do that? Well, Reach offers us this launch token. Right, launch token is how we're going to do this. We're going to say const the NFT. I know we're creative. I have to be very literal with my constant names. Await the standard library to launch us that token. What do we need to know? Well, we need to know who's creating it. It's this account creator. What we're calling it. And we also need to set the supply. There are a couple other optional methods here, but we're just going to say there is one for the supply, and that is in launch token. We're not going to get too far into that right now. Okay, so there is our NFT. There is the supply. Well, let's get the ID. The NFT ID. Well, it's going to be equal to the NFT's .id number, which is going to actually return the ID number from the back end. Now let's say const the minimum bid that we want to allow is, again, this is a currency, right? We're going to say, let's say it's 2. We want to allow 2 algos. Well, you can't just type 2. You need to tell Reach to parse that currency down to micro algos. The network, the Algorand network is going to transact in micro algos. So Again, you can hard code micro algos or use the parse currency function to actually allow Reach to take what you, the programmer, want to do is 2 algos and parse it down into micro algos, right? Well, we also need to set the length in blocks of our auction. Well, I want to say it's 10 blocks, right? We need to define what the parameters are and store those. Well, we're going to store those in that object. Remember, it needs to have a couple different definitions inside it here. So let's put it inside an object. Let's say the NFT ID, the minimum bid, and again, the length in blocks. So that's going to store all of our information inside of this object called parameters, right? So before we return back to the back end, we're gonna define the creator's interact object, right? This object will be created after the bidder's API logic, which is actually covered in the next section. But let's go ahead and define our front end here, creator interact object. Give myself some space here. I'm gonna jump down to say 51. Now let's actually create here. So let's say this contract creator info. I try to catch all my syntax errors, but if you see one, please holler at me. Remember, we need to attach that to that contract, to that back end that we had set, that back end constant we set, right? So now we're talking the contract info for the creator. Well, we're going to use the account creator to actually attach to that contract backend, right? Line 52 here, we're going to wait. We're actually going to instantiate this object. Right. Go back and add these now so I don't forget. Well, remember, what does the creator need to do? Well, this is the back end. Well, the creator needs to get sale. They need to auction ready. They need to see bid, and they need to show outcome. Okay, well, how do we make that happen? Well, to get sale, well, that's a function that takes in no parameters. Again, jump down, let's get that. How are we going to do that? Well, we already put it in an object called params. So why don't we just tell the console, this is what's going on. Creator sets parameters of sale. And then we're going to pass those params in. And we're going to return those same params to the backend, right? So what did we say about get sale? Well, we said that get sale was a function that took in no arguments and it returned us an object. That object had the NFT ID, it had the minimum bid, and it had the length in blocks. Well, let's look at our params. What is get sale doing here? Well, it's taking in no arguments and it's returning params. Well, we up here said that params was already the NFT ID, the minimum bid, and the length in blocks, right? So now you can start to see how we actually define these data here. We declare them back here. We say length in blocks is an unsigned integer. But here we actually say length in blocks equals 10, right? This is how we mirror the back end and the front end, right? Now let's go back down here and continue on with our interface, right? So line 57, we're going to write the functionality for this auction ready. Well, that also took no parameters. What did auction ready do? Well, auction ready is just going to go ahead and start our bidders. Right? We'll get there. We'll get there in a minute. So if you're not familiar with where that's at, I'll get to it. Well, we also need to see the bid. Well, see bid takes in, what does see bid take in again? Oh, it takes in an address and an unsigned integer. Okay, well then let's give it the address of whoever is calling and the amount that we're going to set for it. Right? Okay. How do we do that? Well, we're just going to, in this application, again, these terminal applications, it's very easy for us just to kind of output some stuff to the terminal quick so that we can see what it's doing. And then later when we need to implement that functionality with the actual GUI front end, we'll do so a little bit differently. Okay, so here we say that the creator saw that, well, we need to say who it was. Remember, it's who, but we can't just say who. We need to say, we need to let the standard library format the address of who, right? So here, you know, we're putting it inside this variable, these variable brackets, but here we're actually allowing the standard library to format that address for us so that we can read it. Well, what did they do? They bid. Well, they bid. Well, how much did they bid? And here's an option. Here's a chance for us to talk about this. How much did they bid? Well, they bid in algos, right? So if it comes as micro algos, we need to format it back to readable algos. Because you don't want to be reading all these in micro algos and think that you're paying in the millions. You're having a lot of troubleshooting support around that. So if we need to take our currency from algos down to micro, we use parse. If we want to take our currency from micro back up to algos, we use format, right? Okay, well, that's our C bid. What else is left? Show outcome, right? We need to show the outcome. Well, that's going to take in whoever we set to be the winner, whatever amount they won with. And then we're gonna, here we're also gonna give this a console log where we just say that the creator saw that, well, again, it's the winner, but we need to do a standard library format the address of the winner, right? What did they do? Well, they won with, well, standard library dot format currency. They won with the amount. Right, so reach is already, here's a couple more key abstractions. Again, like this is math you usually have to do. This is an abstraction for reach, where they're allowing us these nice, pretty readable formats for our addresses and formats for our currencies, right? Okay, well, that is the creator interact object there. And those are the functions that the creator is going to have. Again, they mirror what we declared here, right? So again, I've hammered on this a lot, but I'm gonna continue to do so because it really gets you thinking in this way. That comparing the interact interface in the back end RSH file with the interact objects in the front end, it's apparent that the back end functions are mirrored, right? The signatures on the back mirror the functionality on the front, right? So now we've defined the initial data points, what those look like, and then we're going to turn to the communication model. Communication model, this controls how our participants actually interact with one another and with the contract, right? We have a roadmap for this because we did our problem analysis, right? This is why we do problem analysis. It allows us to more easily see the flow of our program before we try to write it. And that allows us to write tighter, more efficient programs. It's something that every software engineer, everybody aspiring to write these full-size programs should be doing. Take time to stop and think about how your app should actually be put together, right? So again, per our analysis, the creator, who is a participant, submits the NFT to the contract, and then bidders, who are APIs, right? These are API participants. They begin to bid on that newly posted NFT. Highest bid gets held by the contract. New bidders must make a higher bid than that. As these new bids are submitted, the contract returns the outbid back to that API participant, right? So finally, at the end, we're gonna announce a winner of the auction, announce the highest bid amount, and then we're going to transfer to the creator in exchange for that NFT. NFT goes to winner, algos go to creator, right? So what do we mean? Participants, API participants, right? I've touched on it a few times, but this is a key abstraction and reach. And when you start to write programs that involve more than just two participants, this is key, right? So a participant is a user who takes part in the dApp and can have persistently stored values in its local state, right? Participants are associated with an account address on the consensus network, right? Again, here we just mean blockchain. API participants refer to a class of participants who share the same functionality. Every bidder is only going to need to bid, right? So let's think of another application, like where everybody's voting on their same or on their favorite color. There's an unlimited amount of voters who can participate in voting, but all they need to do is vote. Well, in this example, we would create them in an API and we would just call them voter, right? But similarly here, we have an API of bidders where the bidders, all they're going to need to do is bid, right? APIs are unique because they represent the front end pinging the back end only when it's needed. And when we use APIs, we allow you as Reach developers to create more quiet and efficient programs that are not as computationally expensive, right? Now, a key point here is that you must always have one participant because APIs cannot deploy contracts. Remember, we need to deploy that contract to the network before we can use it, right? Well, APIs cannot deploy contracts. Participants deploy the contract, right? So here again, the creator is going to deploy, the bidders are going to attach it and submit their bids, right? So now let's actually codify what we keep referring to here as the communication model, right? So let me go back to my RSH file here, make sure I'm in my RSH file. We're going to start down here on line 19. We're going to say that the creator only. What is only? Well, it's not the bidder, it's the creator only doing something. This is what we refer to as local step. If I am using this application for real right now, I would be sitting on my side of the computer inputting. Well, what am I inputting? I'm inputting the NFT ID, remember? I'm inputting the minimum bid that I'm going to allow, and I'm inputting the length in blocks that I'm going to allow, right? Well, how do I get that information? Well, remember, that's returned from get sale. Okay, well, how do we get sale is not back here. We can't use this get sale, right? This is just the method signature. The functionality exists up here, get sale. Well, to do that, we need to interact get sale so that the creator interacts with their front end function get sale. Now, this is going to return hashed values. This object is a hashed value. Remember, we sent params, and hashed values in Reach need to be declassified before we allow their use. Right? So, what do I have here for an error? I have an error that I shouldn't have. Oh, unused. Yeah, I'm not worried about that yet. It's ahead of the game. We will use those values. So, again, the creator is going to input that information, and then the creator must publish that information to the consensus network, to the Algorand network. They're going to publish the NFT ID, they're going to publish the minimum bid, they're going to publish what they want for length in blocks. Well, I must have referenced it somewhere as a single because I just got
In your creator, yeah.
Yeah, there it is. Somebody cut me. Thank you.
Yeah, I was getting the same error.
Yeah, it happens, and like I said, especially in these presentations, there's always some like minor error. But if you watch Reach pop those things up to you, it will help to make sure that those errors are less frequent. Okay, so now we're going to publish all that information to the blockchain, right? We're going to set the amount. We're just going to set a constant for the amount of NFTs that we're selling at one. And now we're going to do a common thing here in Reach, and we're going to commit. What does that mean? Well, that means that we're moving away from this consensus step. right? We need Reach to know that we're done publishing to the blockchain. We need to move back to our step, which I, the programmer, am going to tell Reach what the next step is. Well, the creator is now ready to pay the amount of NFTs and that NFT ID into the contract, right? To pay, that NFT is now deposited into our smart contract, right? How many? Well, just one that we set. All right, so now line 26, we're going to create the interaction here with what we've defined already as auction ready, because we've already put in all the information we need. We're going to need to tell, remember, auction ready is a front end function, right? So we're going to tell it, well, we want auction ready, but we can't just do that because this is a front end function. We need to interact with it. We need to interact with our front end and tell us what this auction ready does. Remember, it returns no value. So what it's going to do is just start our bidders. We've yet to implement that, but we'll get there. So auction ready. Well, at this point, this is a key point in the program, right? I've touched a little bit on them, but we're going to talk more about pay and publish. These are common consensus methods, right? And these are used to actually write information to the blockchain. Pay allows the participants and APIs to pay the contract or to pay each other, right? And when we pay, we need to explicitly name the participant because we are going to have to charge them for that consensus action, right? So if we need to write information, we are publishing to the blockchain. Both of these are consensus operations. This is for information. This is for value, right? Okay, so at this point, we've got our creator, we've got our bidder, and we've got the creator having the application ready. I'm sure this is saying that exit cannot be used, and Reach is going to tell you about these as you write your program. Hey, you can't do this. Hey, you can do that. Make sure you read these. These have a lot of good information about errors in your program. So now let's jump to the parallel reduce. This is a huge abstraction in Reach, right? So we could create a loop here with a fork statement that's based on the different cases where bidders are either the new highest bidder or they must bid again. That would be a lot of work. But what Reach does is package all of this into what we call a parallel reduce. Parallel reduce manages all of those forks and updating those API values with that parallel reduce. It creates a race between different bidders and enables our DApp to update the highest bidder in a consensus step until our auction is over, right? Where does the name come from? Parallel reduce, what does it mean? It comes from the fact that our participants are trying to produce a new state from the current values in parallel, right? So it's essentially a fork and a case loop, right? So while Alice is producing a new state, Bob might also be producing one. Reach determines who tried to update the state first, which fork, and depending on the winner of that race, runs the specified logic that we give it, right? So let's start getting into the actual creation. So on line 28, I'm going to define when the auction is going to end. Well, the end of the auction is last consensus time. Now, this is going to return us the last time from the consensus network. Remember, we need to know that because right now, my app is not being deployed. When the app is deployed, I'm going to grab the last consensus time. I'm going to add our predetermined set length in blocks. Okay, now line 29, we're going to create the parallel reduce here. Parallel reduce updates. I'm sorry, that's not the right. Yep, there it is. Now, the parallel reduce is going to update these values at each return in the parallel reduce. Well, which values do we want it to update? We want it to update the highest bidder. We want it to update the last price. And we want it to update is the first bid. Right? This is it's an on-off switch. We'll show you what this is for in a second. So now we are actually going to say that is equal to our parallel reduce. And we're going to pass in these values. Creator, minimum bid, true. What are these values? Well, right now the highest bidder is the creator, so that if we need to, we can send the NFT back to them. The last price is our current minimum bid. And is this the first bid? Yeah, that's true. Right? Reach requires, anytime we deal with loops, to have a loop invariant. What is a loop invariant? Something that must be the same before, after, and during your loop. Loops present vulnerability in your contract, an area where someone could change a value. So we have security around that, where we say that during every iteration of this loop, it is invariant that the balance of our contract contains one NFT. That's what the invariant says in English. It always must contain, the balance of the contract must contain this NFT ID and this amount of them. Remember, we just said that's one of them, right? But you can set another invariant. Loops are very powerful in reach. And that's why we have these abstractions like parallel reduce here, right? So this is going to state that our balance is equal to, well, it needs to be equal to the first bid or the most recent price here, right? Because it's also going to contain, yeah, it's also going to contain the amount. So let's say its balance is equal to, well, if it's the first bid, we're not going to have any balance. Otherwise, if first bid is false, give me the last price. Okay. So now let's actually initialize our while loop. While last consensus time, remember this is just going to grab that from the network, is less than or equal to our end. This is our conditional. We're going to run this loop until our bid is over, until our auction is over, right? We told it when that was, right? Okay. Now, let's call our bidder API. What's going to happen while we wait, right? While our bidders are going to be submitting bids. So we're going to call that an API. Now, this is a special note here. This is an API macro with the underscore there. There are several different features with the API macro, but what it's going to do is allow us to create a check for consensus operation. It's the same check for consensus operation and for a local step. So it's a little bit less code that we have to write the same condition twice. Okay, so here we're going to call the API bidder, right? The bidder API, I should say. So I went over our last consensus time. Again, it's just going to grab that from the consensus network. I went over the invariant. It states that these properties will not change before or after our while loop. This must always evaluate to true, right? Again, these only need to mention values too that may change during execution.
So Nick, where is it checking the balance of? So when you run balance, that's a standard function in reach. When you run balance, it's checking the balance of the contract.
Exactly. Yes, this is different than your front end balance, account balance, right? So that is something that I feel that sometimes gets lost in our comms. We're checking the balance of the contract here, right? So here it says the balance primitive returns the balance of the contract account. Each application is actually given, each smart contract is actually given an account number. That's what it means when it says of the contract account of the D app, of the DApp, right? So the application itself has an account, and we're funding that account with an NFT and with our bid.
So
Right.
is that NFT sitting in another wallet that is like a temporary wallet made by the contract, or like where would that, if you were to look at that NFT on like Algorand Explorer, where would that be showing up at the time? Like if you could,
It would be showing up in the account address of your smart contract.
Okay.
Each contract's actually going to create an account. It's going to create a whole account for the contract. And remember, the creator here is actually paying the NFT, one of them. Remember, pay goes into the contract. So here the creator is giving the contract the NFT. How many? Well, it's giving it one, right? So let's, oh, I see my notes here. We're gonna skip like the actual definition of this line 38 for a second. We'll come back to that. So let me finish writing it here, and we'll say it's called the bid, and it's looks like this. Okay. Make sure I got my syntax right. Again, I don't like making syntax errors, especially while I'm writing code here in front of you guys. But so line 39 here. So we're going to skip line 38, go to line 39, and we're going to actually return. Now, these parallel reduce, they update these values based or via this return statement. So you're not going to see another var update, this equals this, but you may see that these values change. So we're going to return the bid with the notify, set that equal here. Actually, I need to close that one. Okay, so now we'll say, well, we called it notify, and what we want is the highest bidder and the last price. Well, if it's not the first bid, what do we want it to do? Well, we want it to transfer the last price to our highest bidder, right? This is a common call here where we're telling Reach who is this. Well, this in Reach refers to the caller of the contract, right? So in this example, whichever bidder, it's going to assign that person to who. So that's going to change based on who's actually calling it. Creator.interact. Well, we want them to see the bid. Now here's where we're actually going to update these return values. Well, the bidder is going to be stored in who. What they bid is going to be stored in bid. And then, well, it's no longer the first call anymore, so we're going to set that to false. Right? What are these values? Oops. What are these values here? Well, it's the highest bidder, the last price, and is first bid. The highest bidder right now is whoever that was. That's their bid, and it's no longer the first bid, so let's call that false. Right? So this actually closes our API here. This closes our return. This return up here, that actually closes the API macro. So let's talk about timeout. Let's talk about timeout a little bit. So next, we're going to provide a timeout to the parallel reduce. Right? This allows the parallel reduce to escape. So it's triggered when the end of absolute time resolves to true. So when the timeout's triggered, creator will move our app from the consensus step with the publish, and the app will return the values for the highest bidder, the last price, and it's the first bid. So after our API here, we're gonna go down and say timeout. Well, we're gonna use absolute time. There is a few different time methods in Reach. One of them is absolute time. Okay. Line 49 instructs the trigger to timeout, or instructs the timeout to trigger when absolute time reaches the value stored in end. Then line 50 here, we're going to actually need to publish. Remember, the creator needs to move us out of consensus, move us into consensus, and actually to be able to return these values. This is the continue of a parallel reduce is inside this return. So Reach will tell you that it requires continue to be in a consensus step. Continue is contained inside of return. So if you've done other while loops that don't look like this, that's why. We're going to update all of these values, and we're going to call this is the first bit. Okay, so that's our timeout. We're going to close the timeout method there on 52. Okay, so now that the timeout's closed, let's go back to the front end bidder logic, right? Front end is contained here in our index.mjs, right? We're gonna go to up here where I left a bunch of space, and we'll start here again. Line 17, we're gonna create a let for done. This is common in a lot of different programming languages. We're gonna create an array for our bidders. Right? Okay, well, now we're going to create that function we saw earlier, start bidders. Well, it's an async function because we need to use it with a wait. JavaScript does not allow us to leave that out, so we need to put that in. Okay, so down here on line 20, we're going to start by creating another variable for the bid. We're going to store a bid in a minimum bid here that we've already determined, right? We're going to say that it's 2 up here. We're going to create ourselves a let inside of this start bidders function. And then we're going to run another function here. We're going to call this one run bidder. This is another async function. This one's going to take in the address of who. I think that's going to want me to cover. Yep. Sometimes I get the syntax mixed up between my two files, but it should tell you if you're having any mistakes like that. So we're going to create the run bidder, right? We're going to say const increment. We're going to say parse currency. Remember, we need this to bring it down from a random number. Well, random to 10. Some of this stuff we're baking into the logic because we're not actually allowing our users, we're creating test users. So some of this logic is based on that. So don't get too hung up if it's, oh, well, we're creating a random number for the bid. That's just so that we can have our MJS file interact with it quickly, and then we can actually sort of quickly produce these outputs that we're looking for. So, okay, now let's add that increment to the bid, and that's where we are. So now, line 23, we're gonna go ahead and say the bid is, we're gonna add the increment to our bid. Then on line 25 here, we're gonna say the account is equal to await the standard library creation of a new test account. Well, we need to fund that test account with, no, not start. We need to create with the starting balance, remember? We're gonna enable a debug feature here that's gonna just help us with some error messages if we need so, if we need any of that help. That's line 26. Line 27, we're going to return a promise here. We're gonna await the account. We're gonna await token accept. Remember, we need to opt into these tokens on the Algorand network. So that's what this is gonna do. Okay. Okay, so line 28, we're going to use some standard JavaScript here to use our bidders array. We're going to push the account or who and the account, I'm sorry. Okay, let's create a contract. Let's say remember we have to attach to the back end. Well, we need the creator's info. That's just as we did need Alice's info. Do that there. So, well, now we want to get the balance. We're going to store that in get val. Remember that needs to be async because we're going to await it. We need the standard library to format our currency. Remember that takes us back up. When we need to display the balance, we need it to display in algos, right? Oh, I'm sorry, I believe I pulled that from the wrong line there. Okay, get val is async. It's just format currency from the standard library. We're going to await the standard library to tell us the balance of the account. Okay, so let's give us a couple basic console log messages now. Console.log who outbid. Oh, I'm sorry, I got my lines mixed up there again. We still need who. We want console.log who actually decides to bid. Again, this is all your sort of just front-end command line interaction. We're going to need to format the currency of our bid. I think the backspace is my favorite character. I type so fast, I'm always going back and backspacing. So forgive me if I'm sort of smashing the keyboard quickly. Console.log. Well, what do we want to know now? Well, now we want to know who has a balance before. This will just tell us a little bit more about the way our contract takes out balances and where our funds are actually coming from. So that's actually going to print the balance here before we interact with our contract. So we're almost there. I need to take about a 2-minute TV timeout here. So give me just a second. Let me, and I'll be right back in about 2 minutes.
Yeah, I'll take up here for you. So any questions from anyone about the parallel reduce or invariance? I know we had some questions in the chat. I think I've answered all those. I wonder if we have any other questions in the room.
Oh, actually, I didn't understand the return function in the API macro. Means how it is constructed and how it gets executed. Actually, I couldn't understand. I'm
Yeah.
trying val reduce from last 2 days, but I couldn't get it properly.
That's great. Great question. Thanks, Thosar. Yeah, it would be convenient if we actually had the return statement here on the screen, but such as it is, we have a guide and GitHub discussions on the parallel reduce. Definitely check that out. Jacopo, yes, this is recorded and we'll share that in the Discord. So what your parallel reduce is doing specifically in that return statement is use that return to update the values. And so parallel reduce, because reach primarily is your values that you declare are immutable in most cases, right? And so you see us using const in almost every variable. You hardly ever see, well, we never use vars. Sometimes you'll see a let, very rare, and that is only in the while loop, right? Where we set our are let for the values that can be updated. Everything else is a cost. And so the parallel reduce uses the return to update those values. A parallel reduce is a combination of a fork and a case. And essentially what that means is a fork is like a branch, right? A branch in the road, we can go one way or another. And then a case says, this is when you go to the left and this is when you go to the right, so to speak, right? So like this is when you decide when to take one fork or the other fork. In the documentation, we have quite a bit dedicated to the parallel reduce. I would suggest studying the structure and the syntax of the parallel reduce, understand the architecture of the parallel reduce, and then look at other examples. So our RSVP example in our source code has a parallel reduce that you can definitely check out. And I think you might find that helpful. So when Nick gets back here, I'll find those links and I'll share them in the chat. And are you ready, Nick? I see you hit in the chat.
Yeah, I'm back. I was just grabbing a question there in the chat. You know, for those of you who are joining late, we will make the entire recording available after we finish up here. It takes a little bit of time to get our videos uploaded, but we'll get on that shortly after and have it posted later today. So where did we leave off? Well, we left off here at sort of the end of our creator's communication construction, right? So this is where we're actually defining what our communication looks like, right? So we've created the first half of this bidder's communication model. We've now given the bidder logic that dictates their behavior when interacting with the contract, right? This communication model allows these bidders to race. They enter a race with one another and ensures that they are aware of the highest bidder and the API, or the, I'm sorry, and the bid to actually beat, right? We do this with our parallel reduce and our API, right? So again, a clearly defined communication model is extremely important because there is no middleman in Web3, right? We deploy our contracts ourselves. There is no middleman, there is no maintenance. So decentralized applications create an opportunity to reduce fees and increase the velocity of communications and funding, right? So in this case, instead of actually waiting for the highest bidder to wire credit, the network tokens are escrowed the moment the bid is placed, and they're transferred the moment the auction closes, right? If I was trying to transfer these funds to you via ACH transfer or bank transfer, you're going to have to wait 3 to 5 days. Here in Web3, we can let our contract handle those values in and out, and it can happen automatically, right? So next, we're going to talk about assertions in Reach. Assertions can be static or they can be dynamic. Static assertions written with the assert keyword in the backend are always true throughout the life of the application. Dynamic assertions may vary in truthfulness based on the state of your dApp. So dynamic assertions in a local step use an assume and a require in a consensus step. But Reach has actually removed the need to remember when to use each one with the check method. Check will automatically determine which mode of the dApp is in, you're actually in, and then it'll use the appropriate dynamic assertion for you. So let's return to the missing pieces and let's populate them with our actual assertions here. So missing pieces of our RSH file. Well, up here on line 27, we have a missing piece. What is that missing piece? Well, we need to assert. We need to have the Reach verification engine check something for us. What do we want it to check? We want it to check that the balance of our contract, remember, balance is calling for the contract, contains the NFT ID. How many does it contain? Well, it contains the amount that we told it. But what happens if that's wrong? Well, we're going to say the balance of the NFT is wrong. Right? This is a static assertion. It asserts that the balance of the NFT will always equal the value stored in amount, which we've set to 1. And if this assertion fails, the program will exit with an error message of the balance of this NFT or of the NFT is wrong. Right? Where else do we have? Well, line 38 down here, we have another break. What do we think we're going to need here? Well, we're going to need another assertion. This one's going to be a dynamic assertion. We're going to be able to use check here because Reach will be able to tell which state the app is in and which version of check it needs to use. So we just say check. Well, we're going to check that the bid is higher than the last price. Right? If it isn't, if this is false, tell us the bid is too low. Return that the bid is too low. Right? So here's another example, right? This is our dynamic assertion. What doesn't it like? Oh, is this oh, I'm sorry, I think I have an error here. 38 check. Bid. Last price. Bid is too low. Oh, I have an extra. So that maybe. Syntax. Don't forget your syntax. Okay. So again, this line 38 is going to go over a dynamic assertion. It's going to provide a local assumption that the incoming bid is greater than the last price. If false, tell us the bid is too low. Right? The API macro negates the need to use a repetitive check inside the return. Right? The compiler knows that API indicates that the local step and the consensus step dynamic assertions are exactly the same. So this is the only check required in this parallel reduce, right? So that concludes our back-end assertions. Now we're going to implement a try and a catch condition in the front end, right? So where did we leave off? 33. Let's give ourselves 34 here. This is a standard syntax for JavaScript. This is not Reach special. We're going to try. It's a conditional, right? So we're going to try. We're going to store a couple values and constants here, the last bidder and the last bid. What are we going to say? Well, we're going to say that these come from this await, from this promise of the contract info of the APIs. Well, which API? Well, the bidder API and its bid, right? We need to tell the console what's going on here. We need to tell the console that who actually outbid. Well, who did they
En este
outbid?
momento serán todos hackeados, la concha de su madre. En este momento serán todos hackeados, hijo de puta. En este momento le voy a reventar la computadora, la concha de su madre. En este momento van a
Thank you.
En este momento van a ser todos hackeados, la concha de su hermana.
Okay, yep, just use that for everybody. Please keep your mics muted unless you have a question. And I prefer your questions go to the chat so that I can answer them as we flow through here. But okay, anyway, where were we? We were telling the console something. Line 36. What were we telling the console? Well, we were telling it about the outbid. Well, we said who outbid. Well, who did they outbid? They outbid the last bidder, right? Well, what did they bid? Well, they bid an amount that the network has stored in micro algos. So we want to use the standard library to format, well, sometimes you autocomplete the wrong one, to format the currency, right? Where did we store this value? Well, this value is stored in last bid. Okay, so let's close, let's give a period just to close that. We'll close out this. And what are we going to do if this doesn't work? Well, we're going to catch the exception inside of E there. It'll try, we'll actually throw our exception into here if we have an exception. We're going to log what our exception was to the console. Well, what is it? Well, who actually failed to bid because the auction is over, right? It's past our end time. That's what this exception will tell us, right? Now here on line 40, we're actually going to, just another console message. And this one's just going to be about the balance. We're going to print the balance of the bidder so that we can prove their payment either went in or it didn't, right? So who, again, is going to store that, have that address for us. The balance after is, what is the balance? Well, we have a function for that. We called it getVal. So let's await the balance, right? Okay, make sure we don't have any extra lines here. So our app is almost complete. I know that we've gone through a lot here, but let's look at the size of what it looks like, right? It's a lot of spaces there, but you know, about 50 lines of code there, and then on the back so far we're at 54 lines of code, right? So there are only 4 more small sections that we're actually going to complete. So at the end of the auction, our app needs to actually transfer the NFT to the highest bidder and then the tokens to the creator, right? The front end must reflect that back end's transfer pattern, right? We're also going to create a few test bidders and then write the final commit and exit, which will actually destroy our contract, right? This is why we need to verify that there are no balances left before we destroy that contract. We'll write the final commit, we'll exit and destroy the contract, right? So let's resolve these one by one. So transfer patterns, let's talk a little bit about transfer patterns. So a consensus transfer occurs when a participant or the originator makes a publication of a set of public values from its state and then transfers 0 or more network tokens to the contract account, right? Additional transfer patterns we cover in reach guides, but in the logic we're going to implement here, we're just talking about the NFT being transferred to the highest bidder at the end of the auction. And if it's not the first bid, then the last bid amount is transferred to the creator, right? We're just determining which bid there should be actually transferred to the creator. So we're going back to our backend RSH file here, right? We're going to give us one space. And now line 54 here, we're actually going to make this transfer. Reach comes with this. We call it transfer here. Well, what are we transferring? We're transferring our NFT ID. Remember, we're only transferring one, and we set a constant for that. Who are we transferring it to? Well, we need to transfer it to the highest bidder, whoever that is. We have a special conditional here on 555. If the contract is closing after at least one bid, then we also need to transfer that winning bid to the creator. How do we determine that? Well, remember we have a Boolean for is first bid. So this is gonna, if it's not the first bid, let's transfer the last price in algo to the creator, right? If it is the first bid, skip this logic. If it's not the first bid, if this is at least bid 2, let's go ahead and transfer that price to the creator. Line 56, creator is going to actually show the outcome of our auction here. Show outcome, highest bidder, and the last price. Remember, we already defined show outcome. Now we're just adhering to the rules. So we'll stop here and move to the front end logic to create the same transfer, right? So front end logic. I think I have some of this pretty crossed up with where we're at. So let me get my line numbers matched up here a little better. I think I just put in way too many break lines there for me. All right. I think that looks correct. Okay. Now, down here, line 68 here, we're going to say for. We're going to iterate over these. Who and the accounts of our bidders array, remember, what do we want to happen? Well, we want, again, to create another constant here. that has the amount NFT. What is that? Well, it's going to be awaiting the promise from the standard library, balances of, which returns multiples. So the account, no, NFT ID. We want to make sure we notify the console what's going on here. Well, what's happening? We're saying that who has, what do they have? Well, we need to format that again from the standard library. We'll use format currency here to format our amount, right? And then we're, based on our consensus network, we're gonna use the standard library function standard unit. And this allows us to use the standard units of the network that we're on. In this case, Algorand is the network that we're on. And the amount of our NFT. And then we'll say of the NFT, right? And the orange here is that where our actual comments, what's actually going to log. And then here's where we're formatting different numbers and amounts so that it's easier for you to read. So it's easier for users to read, such that we use our functions, our standard library helper functions that reach create for us, right? Okay, so now that is the transfer pattern defined for the bidders, balances are tracked, and what's included in each transfer, right? A firm understanding of the economic model of your DApp is required to create these decentralized applications that exchange our network tokens like we expect they do. It reduces the opportunity for dishonest participants to exploit your ecosystem, right? So in this DApp, the NFT is transferred to the contract at the moment the auction is created. The bidders transfer their tokens to the contract the moment they place a bid that's higher than the previous bid. And then the contract returns that bid to the bids to the creators when they've been outbid. So if I've been outbid, the contract's not going to store your bid. It's going to send it back to you, right? So at that time, when the auction closes, the contract transfers the winning bid amount to the creator and the NFT to the winning bidder, right? So here, we're actually going to use some of this space that I've left open. Let's go back to our MJS, to our front end here. On line 43, this is where we're actually going to create our bidders, right? Remember, they are stored in this function here. This is how we start our bidders. So we'll start our bidders and then we'll run a bidder when we pass in who it is. So let's say down here on line 43, we're going to await run bidder. Well, who are we going to run? Well, let's say Alice. Keep our naming conventions familiar. Await run bidder. Well, who are we running this time? Again, let's say Bob. Then let's create another one. Let's say that this is Claire. I think common third participants, Claire. A good name. While let's say while we're not done, remember we set done to false here. While we're not done, what do we need to do? Well, we need to await that the standard library wait function, which allows us to wait a certain amount of time to do these things. This is a helper function in reach. Okay, so what this is going to do is it's just going to loop us forward this one block, right? Wait one block until the auction is over. So that's all there is to this step, right? That's our create bidders. Let's loop through them until our auction is done, right? So on testnet or mainnet, We're going to ask our bidders again to connect their app to the wallet, or their wallets to the app. But this guy tests on the dev net, right? This is a Dockerized, this is why we have Docker. It creates you your private dev net, right? So in here, we need to create these participants, right? To test the functionality of our app, to work out the bugs, right? So this is where we're doing this, right? So with all the other tasks that we have complete, we need to end the contract. That is an RSH application, so that's part of the RSH file. So we're going to go down here at the bottom. Remember, we do a lot of these. We do a lot of commits, right? And that's going to move us into the next step of our application. Then we're going to exit. What is exit? Exit's actually going to destroy your contract. Each contract instance that runs is its own alive contract until you destroy it with exit, right? One final return to the front end here to provide our bidders with their actual exit. So let me get back to the front end here. I think I have some extra lines from what my guide is telling me here, but we'll see if we ended up missing anything of what the contract doesn't like. So okay, so down here, say down here at the end, we're just gonna say our variable done equals true. And this is something that we've told the contract about. I'm sorry, we've already defined it as a let, so we can't do that again. Remember, we let it up here to say done equals false so that we could change this value throughout. Well, now we're done, so let's set it to true. That's it, right? So that is the full Reach application that simulates a live NFT auction using our APIs, right? I'm going to go back up here and show us our API, which is our bidder. And it allows us to use this parallel reduce to update, use our looping, our abstract looping structure here to update our values based on different forks that could possibly happen, right? That's what our parallel reduce is running. So let's see what happens here if it actually wants to run for us. Okay, so we're going to get into the folder that I'm in here. What's in here? Index.mjs, index.rsh. Let's hope that it actually compiles for us. If it doesn't, we're just going to work through the error messages. Really, there must be an error in the MJS file because we don't often get through an entire presentation with no errors. So let's tell Reach where we want to run. Let's actually run our application. Now, if you have errors in your MJS file, this is where they're going to start to come out. You know what? I don't think I actually saved those files. So maybe that's the problem. You don't need to run compile every time. I like to just to sort of pick out where my errors are. So let's hopefully we get some output messages from our actual app here, and let's give it a second to do everything it was supposed to. Remember, everything we did here was automated. Now you're going to change this functionality if you were to actually implement this with a front end where you're going to ask real users to click buttons. So what did we do? Well, we created a test account for the creator. The creator created an NFT. I mistyped parameters here. But the creator is setting the parameters of the sale. Well, they're setting the NFT ID, the minimum bid, the length and blocks. And then we're going to have our bidders actually start to bid on the NFT. Well, Alice decides to bid 4. Here is her balance before that. She outbid our original bid. Well, our original bid, remember, was just 2, right? Here is the balance after, right? She's paying that actual balance into the contract, right? Well, Bob bids 9. He outbid Alice's 4.0, right? So here's back and forth bids. And now we say, well, it failed to bid because the auction's over. So this is us testing that end variable. when do we want our auction to end? Well, we tell it when we want it to end. And after that, we need to handle the exception where we tell our users that, hey, the auction's over, right? So now we get through our creator seeing who bid what. Here's the first bid of 4.079, and then here is the winning bid. Here is our user's wallet. This is how we identify users on the blockchain, their network, their actual wallet address. They won. Okay, well, here's so far what's happened. Alice gets her 99 back, right? She's got 0 of the NFT because she lost. Well, Bob, he won with his bid of 9. So we took 9 off of his total, and then we transferred that to the NFT to Bob. So he lost his algo, he paid, and then he actually was returned the NFT, right? And now we say that Claire also has 99 because she failed to bid, right? And that is our NFT auction app. That is the output from our command line. And that is how we build that in Reach. So that is everything, right? So the app behaves as we expected it to. The creator creates it and sets the parameters and all that, and our balances update appropriately. These are things that we need to check for in our MJS file. These are the things we need to check for in our command line applications, right? What next steps could there be? Well, we could make it interactive, where we actually allow a person to input bids, right? And that's a little bit closer to what a real life application would look like. So, you know, to wrap here, that is successfully the NFT auction using APIs with Reach. I'm going to go ahead and look at this smart contract again here, because I do think that this is very powerful. What did we do? We actually implemented NFT auction. We actually implemented an NFT auction in Reach. It's 59 lines of code with some extra spaces. I know I put extra spaces all the time. 59 lines of code for us to actually deploy this code to the Algorand network and allow our front end here to make calls to that contract and execute it. So if I stripped out all the blank spaces from this, you're probably looking at another 60 lines here, maximum. So 110, 120 lines of Reach code. And we were able to implement a full NFT auction app. So that is all of the content I have for the session. I thank you guys. If you come in the beginning and you stay for the whole thing, thank you. If you can make it for any amount of time, I appreciate you setting aside your time to come in and learn a little bit more about Reach. So at this time, we'll tackle any questions that are left in the chat or any questions that you'd want to ask directly. Now's the time for that.
Yeah, I think we stayed current with all the chat. So yeah, anyone has a question, go ahead and ask now, or we'll close soon.
I just love that. I know, and again, anybody, please feel free to jump in and stop me, but these Reach applications have so many features packed in because of the abstraction. You first look at parallel reduce and you start to think about why is it like this? Why is it so complicated? Well, it has so many features packed into 20 lines of code. And that's really the real functionality of what's going on in our Reach app that allows all these race conditions and our API functionality. That's a pretty impressive level of abstraction. Thank you. Me and the mustache both appreciate that. I'm starting to believe that the mustache is actually becoming famous. And
I think it's part of your personality.
Yeah,
You can't get rid of it now.
Hello.
yeah,
Can
go
you hear
ahead.
me?
Yep.
My name is Teddy.
Hi, Teddy.
Thank you for the presentation. So when you say that Reach is an abstraction, is it like it's a higher level off of some, what's the underlying code?
Well, it breaks down into JavaScript. So remember at the beginning, I said that our build folder is going to contain index.main.mjs. So let's look at that. So here is what Reach actually breaks your code down into, right? This is the JavaScript. It's JavaScript, basically. MJS stands for modified JavaScript. It basically breaks down into JavaScript, but let's get to the end of our file. And you'll see some of these things, you'll start to say, well, this object had a length and blocks and minimum bid and an NFT ID, but this is how far Reach breaks down your code. How many lines are we at? Look at this. We're 1,076 lines of code. We didn't have to write that. We wrote 59 lines of back end and 50 some lines of front end. So when I say abstraction, I mean that Reach is an abstraction of, it's not exactly JavaScript, but it builds on top of, right? And that abstraction allows us to create smart contracts with all of this extra functionality. You can go do this in Teal, but you're going to have thousands and thousands of lines of Teal, and you're going to have to remember the stack execution language that is Teal. So when we say abstraction, we're abstracting all that away and making it easier for you to write smart contract language. And that's what Reach is built all the way around, is smart contract language. So that's what I mean when I say abstraction, is we're abstracting away that native blockchain language, and we're abstracting it into Reach, which allows you to write shorter, more compact, and easier smart contracts.
This one was particularly, when you mean contracts, are there any other type apart from what you've done today?
Well, when I say contract, I mean, this is what's actually deployed to the blockchain, right?
Yeah.
This is not. Your front end MJS file does not end up on the blockchain, right? This is your website. This is your graphical user interface. This is where users are interacting with your smart contract, but this is your smart contract. This gets sent to the blockchain. Remember that graphic I showed earlier, and maybe I can bring it back up, but that graphic I showed earlier of it actually being deployed to the blockchain, that's what I refer to when I say smart contract. So whatever you write in this backend.rsh file, when I say smart contract, that's what I mean, because that's what actually gets deployed to the network, and that we aren't able to maintain after that deploy happens.
Thank you.
I don't know of any examples for ARC20. I'll make a note, see if I can find any. I'll drop them either in the Discord channel or, yeah, most likely the Discord channel. If you came to us from Twitter or somewhere else, please jump in the Reach Discord. We really do get into it a lot there about the nuances of the language. If you have some features maybe you're requesting, or if you have like a technical question that you really need answered, the Reach Discord is the best place to have that answered. Drop that in the chat here. But yeah, I'll check that out. I'll see. I'm not completely aware of ARC20 examples, but I'll see if I can find any. The Reach, the public repository of what's being built in Reach is still evolving, right? Especially after, I said that we update the language every other week. So as features are rolled out and things, like, we're constantly updating. So we do see a lot of users say, hey, what happened with this update? And things like that. So it's best to stay up on that in the Discord.
Thank you.
Yeah, absolutely. Thanks for the question. Yeah, okay. Yep. Troubleshooting the parallel reduce can start to get tricky. A lot of things are happening simultaneously in short, compact sections of code. So yeah, we can definitely look later. Maybe if you're having some issues with like a specific area of that, we can look at it later. Yeah, there are deprecated methods as they exist now. So to answer this question, we'll in case there is an update to the language, will there ever be a deprecated method? Yes, we deprecate methods as we see an improvement for those methods. For example, let's look at contract. Let me actually find it, the code here. Right here. Contract. This used to just be called, you know, if you were deploying it, we called it deploy. If you were attaching to it, we called it attached. Those are not the best words because it's not actually what's happening, right? What's actually happening is the account creator is attaching to that backend contract, and then we're giving it CTC creator info. So we used to call that deploy, but it's not actually what it's doing. So instead we changed it to contract, and now contract does that same functionality. And you'll get a notification if it's deprecated. I actually think I have a repo in here somewhere that's got a deprecated method like that. But Reach will let you know, hey, that's deprecated. We don't use that anymore. There used to be a different one for init here too, which for the life of me, it escapes me what the deprecated method is. But either way, we'll allow the deprecation to continue for a short amount of time, but then we'll switch to the new method. So will this be on GitHub? Yeah, it might have actually just been called deploy. I think you might be right, Connor. Will this be on GitHub? Yes, it is. It exists there currently. Let me get you a link to that. So this folder here has a lot of good examples of Reach programs. That's the examples folder in the Reach Lang public repository. And then the actual auction app that we wrote today exists in that examples folder inside NFT auction API. Right, this is kind of the base level functionality. We can get all of those features and show what's actually happening inside of one app. So you'll find this example there. Okay. All right. Yeah, I think we're all caught up on the chat. If nobody else has any other questions, I'm going to go ahead and cut it. One of my key feedbacks for myself is that we are way over time. So I need to try to pack my time in a little bit more, but there's so much to talk about. We start getting into what's actually going on behind the scenes, and I love talking about it, so it's easy for me to let my mouth run. So my key critique is to keep this within my 90-minute desired time frame. Otherwise, any other questions? I'll take them here, and we'll go ahead and wrap up. All good. Yeah, awesome. I enjoyed this. I hope you guys did too. I hope to do some more of these in the future. So keep an eye out. We'll let you guys know. We'll post the recording of this soon after we finish. So give us a little bit of time to get the video to actually compile and upload, and then we'll get it sent out on the Reach channel so that you guys can review this whenever it's convenient if you missed any part of it. So thank you everybody for coming. I really appreciate it. Again, we'll look forward to seeing more of you in the future. So thank you.
Thanks, Nick. Very helpful.
Yeah.